Let's look at another area calculation. What we want to do is compute the area of the sphere x squared plus y squared plus z squared equal 225 that's inside the cylinder x squared plus y squared equal 81. Now, when you think about this, we have the cylinder here and the sphere here. And the cylinder actually gives us the representation for r. It's just the disk here of radius 9, which I've written in polar coordinates. But so what we're seeing is that due to the symmetry of the sphere, if we compute this area here, then we can just double the result to get what the problem is requesting. And so again, you're thinking, well, polar coordinates will be a nice way to do this problem. Let's see how it works out. Now, what we want to do is to get a function, so we're going to take the principal square root, solve for z, and write our f of xy this way, the square root of 225 minus the quantity x squared plus y squared. Now, in order to move the problem forward to actually get the actual integram for the surface area calculation here, we need to take some partials. So we're going to apply the chain rule. We'll have 1/2 and then the negative 1/2. And then, of course, the derivative of the x part here, the derivative of negative x squared will give us a negative 2x. So we have that, retire the negative power, and we get a negative x with the square root downstairs. Now, if we do the y partial, it's exactly symmetric, and we get exactly this. So these, again, just utilize the chain rule. Now, of course, we need 1 plus the x partial squared and the y partial squared. So what we're going to do, if we square this, we'll get x squared with no radical, and we'll get y squared with no radical, which we can easily add together to get this. And then we need to add 1, so with a common denominator, we're going to have a 225 minus an x squared minus a y squared in the numerator, which will absorb these two terms, and the only thing left is the 225. So again, these are very standard calculations which you've seen before, but you often deal with spheres in engineering and science, so these are good things to review. Now, in order to finish the problem, we have our 2 for the symmetry here, and also we have to take the square root of this expression to do our surface area calculation. That'll give us the 15 upstairs, and of course the square root of the denominator downstairs. Now, we're going to move from the Cartesian to the polar because that's much easier for this problem with all the circular symmetry. So we're going to have an integral from 0 to 2 pi and an integral from 0 to 9. And of course, we'll replace the x squared, y squared with the r squared equivalent. And now, of course, this is ready to go. These are constant limits of integration, so we can split it up. We have our d theta integral, and notice we have the 15 times the 2, which is 30. And of course, we can work on the r integral too. But notice we don't have a negative 2r here. We just have the r as is required from the chain rule. So we put in the negative 2, and then of course we pay for it. So this integral now is table ready. So when we look at that, we add 1 divided by the new power. Of course, this integral just gives us 2 pi. And when we add 1 divided by the new power, we're basically multiplying by 2 here. So the 1/2 and the 2 absorb, giving us a negative 60 pi. And then, of course, once we have the new power here, we have to evaluate between 0 and 9. So upon evaluation, we're going to get 225 minus 81 square root, and then, of course, minus the square root of 225. Of course, 225 minus 81 is 144. That gives us a 12. And of course, this gives us the 15. So we have the negative 3 times the negative 60 pi, which gives us 180 pi. That is the portion of the sphere inside the cylinder gives us these area calculations, and we have it right here. And we are done.